Hello everyone, and welcome to part 23 of the Trigonometry series. In this video, I really want to talk about the kinds of couple techniques that you'll need to use in problem solving in the further period exam, because often they'll give you problems where the problems are made out of trig functions. For example, say you have something like cosine squared theta minus sine theta equals 1, and you want to know how to solve this. Or even worse, they often give you stuff where inside the trigonometric function, it's not just theta, but theta plus something, or something done to theta. So for example, you would find cosine squared 2 theta plus pi minus sine 2 theta plus pi is equal to 1. And so I'm going to give a run through of the two main techniques that you will need to use to solve this kind of equation, and then I will give you an example question that I will solve basically on recording. So one technique that you need to use is that you need to be able to manipulate the interval they give you. And you might be thinking, interval? Is he pulling this like out of nowhere? Well, the thing is, in further period exams, the questions you find, they'll often have an interval for the value of theta, and it might be something like 0 is less than or equal to theta is less than or equal to 2 pi. And this kind of gives you a limitation on what your final answer theta can be. But this is not helpful when inside the brackets of every angle, you're getting like sine 2 theta plus pi over 2. So what do you do at this point? Well, at this point, first you would do something called a substitution. And I like to call this substituting the u in, because basically you make this equal to sine u. And how do we do this? Well, we just say let u be 2 theta plus pi over 2. And now the thing is, in the process of solving the equation, we will ultimately get to a point where we need to use the inverse sine functions, whether it be on our calculator or through the values we know from the unit circle. Anyway, we'll need to use this inverse sine function, or inverse cosine, or inverse tangent, or whatever. And we'll want to know what is the range of values that our angle can be. And obviously, our angle is not theta, it is u. It is this thing here. So what we will do, what it is important to do, in fact, in many of these questions, is to rearrange this interval to give you a range of values for which u is possible. For example, say we have 0 is less than or equal to theta is less than or equal to 2 pi. So to get something like this, first we would multiply by 2 to get 0 is less than or equal to 2 theta is less than or equal to 4 pi. And then perhaps add pi over 2 to get pi over 2 less than or equal to 2 theta less than or equal to 9 pi over 2. Or rather, this is 2 theta plus pi over 2. My bad. So you would have this u term here, and you'd have a range of values for which using the inverse trigonometric functions would be useful to you. Like, you have a range of angles that could be within this bracket. It's just the thing is, near the end of the problem solving, you always got to remember to turn it back into theta and don't just leave it as u, because I've seen a lot of people lose marks for that, and it can be quite embarrassing once you get your paper back. Alright, so the second thing I want to talk about is using the identity that sine squared theta plus cosine squared theta is equal to 1. And the way you do this is basically, oftentimes they'll give you just a quadratic equation, and it'll just be like cos squared theta plus sine theta is 1. And then like, what do they expect you to do from here? Well, given that you have a sine theta as the linear term, like as in the term which is not squared, it would actually be best to turn this cos squared theta into something you can work with in terms of it being made out of sine theta. Because if you can find just the value of sine theta, you can find theta anyway. So you would make the substitution that sine squared theta, or rather cos squared theta is equal to 1 minus sine squared theta. And 1 minus sine squared theta plus sine theta is equal to 1. And this substitution here is a key part of solving these quadratics. And it's especially useful to know that if you have any number in front here, of course, with the distributive property, all the terms in this part are multiplied by that number. For example, like 6 cos squared theta would be equal to 6 minus 6 sine squared theta. And that is really something that's quite important to remember if you want to do this stuff quickly and accurately. So say we are just going to continue solving this equation, and you might realize that it's a quadratic, it's just a quadratic, and the thing you are solving for is the value of sine theta, not theta itself. You're just solving for sine theta first. You got to see this as its own object, and this is a quadratic equation of that object, of sine theta. So you have, say, subtract 1 from both sides to get minus sine squared theta plus sine theta equals 0. And then normally what I like to do with quadratics, this is really a matter of personal preference, but oftentimes I find that it is useful to get rid of the minus sign on the first term, the highest degree term of a quadratic equation. So I'm going to multiply both sides by -1 to get sine squared theta minus sine theta equals 0. If you notice, going from here to here, we're just flipping the signs of all the terms, so this minus becomes a plus, and this plus becomes a minus. Anyway, you can do that when one side is 0. It's quite useful. And then, say we want to factorize this out, so we can factorize out sine theta, and we get sine theta minus 1. And this whole thing, sine theta multiplied by sine theta minus 1 equals 0. And then you can start to, like, you really got to organize your thinking here, because you have a certain thing here, and it's like, you have multiple possibilities of what sine theta can be. So you would say that sine theta could be equal to the set of 0 or positive 1. And that means theta could be like what you do to this side, you also do to every term in this list once you start working with possibilities. Keeping track of the list of possibilities you have is extremely important. Right, so like theta would be equal to the inverse sine of 0, or, so like this is going to be or the inverse sine of 1. And of course, this would lead us to like 0 or pi for this one, and perhaps pi over 2 for this one. And that's basically how you would solve this kind of equation. That's what they're asking you to do. One important thing is to not fall into the trap of using sine a plus b and cosine a plus b unless you absolutely need to, because these things can overcomplicate an equation a ridiculous amount. Sometimes you simply don't need to use these. The only reason you, I suppose you would be using them is if, for example, you are being asked to prove, say, show that sine 3 theta is equal to like some sine cube theta. I think it's 4 sine cube theta minus 3 sine theta, but don't quote me on that. Might be the other way around. I might have gotten this equation the other way around. Anyway, it's this kind of equation that they'll ask you to prove, and that's where you'll really want to use this. And because like the questions that you'll be dealing with can often come in multiple parts, and they might ask you to prove, for example, that cos 2 theta is 1 minus 2 sine squared theta, and then you'd have to use that identity in another equation. Like, say you had your equation and it was, for example, sine squared theta plus pi over 3, and then minus cos 2 theta plus 2 pi over 3. And of course, one is 2 times the other. Say this is equal to 0. And you proved earlier in the question, like the part A of the question, that cos 2 theta was 1 minus 2 sine squared theta. So what would you actually do with this? Well, the key u substitution to make here is to let this be equal to u, so that this is equal to 2u. And then you have sine squared u minus cos 2u is 0. And of course, you're left with cos 2 theta being 1 minus 2 sine squared theta. You have sine squared u minus 1 minus 2 sine squared u equals 0. And you can check this, but it should evaluate out to 3 sine squared u minus 1 is 0. 3 sine squared u is 1. And so on and so on and so on. I think you get sine u could be plus or minus 1 over 9, blah, blah, blah. Anyway, the key idea to take away from this is that you need to be clever with your u substitutions, you need to be clever about manipulating the interval, and you need to make sure you don't fall into the trap of using these two identities except when it is absolutely necessary, because they make things a whole lot more complicated. And normally, if the question wants you to use this kind of thing, they'll do it in a very guided and controlled manner, and you'll end up with these u's and multiples of u within your question. So that is basically it for this video. I don't have much to do about or much to say about trigonometry after this. I might perhaps make a sort of revision video containing all of the syllabus content on this topic. But if you are reaching the end of this video after watching all the videos beforehand, I thank you very much for staying tuned, because you have completed this course basically. There is a wide array of trigonometry questions on the past papers in the Edexcel website. There are more past papers for the 2009 qualification, and it's about the same difficulty of questions, perhaps slightly easier. It's just that because it's a qualification that's been around for longer, the past papers have been around for longer. You can also get these past papers on any kind of free past paper website that you find. I don't have a good source for it now, but if anyone would like to tell me, that would be extremely appreciated. And yeah, thank you for watching.